Hello everyone. As a part of technical paper presentation for VTC 2021 Spring, I am going to talk about on opportunistic selection of common randomness and LLR generation for algebraic group secret key generation. To set the context to this talk, we all know that security is of utmost importance to any cyber physical system. In order to achieve confidentiality, we can either use cryptoprimitive based methods or physical layer security. In the former case, confidentiality relies on the fact that it is mathematically hard and computationally exhaustive to retrieve the plain text or the message from ciphertext with no knowledge of the underlying key, whereas physical layer based methods are generally keyless in the sense that plain text is somehow hidden in the channel itself by exploiting the physical layer aspects. There is one more category, which is a hybrid of the two, physical layer key generation. That is, exploiting the physical layer to generate a key which can be used at physical layer level as a seed or to perform cryptoprimitive based methods at higher layers. We are going to look into this in more details. Suppose two parties, Alice and Bob, are willing to secure their communication. They might use cryptoprimitive based key derivation methods such as Diffie-Hellman and then use any symmetric key cryptography to achieve confidentiality. As a low computationally complex alternative to this, they may use physical layer based key generation methods to derive a key and then use it appropriately. To do this, Alice probes a known pilot to Bob. Upon estimating the channel, Bob probe backs to Alice within the same coherence block, and this time Alice estimates the channel. They do this multiple times depending on the length of the key they want to generate. As a consequence of reciprocity theorem, if the two probes each other within the same coherence block, both of them will observe similar channel estimates. Due to multipath fading, each consecutive block gives a random channel estimate, that is, it offers statistical independence across the key. By the end of the probing phase, two parties observe a correlated random process, also known as common source of randomness, which they quantize to get a correlated key that is correlated across the two users. In order to quantize the sequence, they use scalar quantizers as shown. This is, for example, a four-lever quantizer having three decision boundaries, and to compensate for imperfect reciprocity or estimation error, guard bands are introduced around the boundaries. Samples lying in the guard band are discarded by the two parties in consensus phase and are not considered for key generation. In order to do that, after the quantization, one of the user broadcasts the list of indices which are out of the guard band at his site without revealing the polarity or the quantizing reason. The second user then simply chooses the common out of the band indices and share the final list with the first user. This comes under the advantage distillation phase. Now they use these indices to get the key, but still the key is not exactly the same at two sites, so information reconciliation is done. To compensate for the leakage while this phase, privacy amplification is followed next. Finally, the two users share a common random key. The case of two user is well studied. So as a baby step, now we will try to mimic the key generation for a network consisting of three users. One of the nodes is declared as a facilitator for the reason we will see soon. We have used symbol H to denote the channel estimate or fading coefficient. Subscript denote the channel link. For example, H12 is the channel seen between node 1 and node 2. H12 and H13 are Gaussian distributed because of the relay characteristics of the fading channel. The protocol is as follows. Node 1 broadcasts the pilot which helps to estimate the channel H12 and H13 at node 2 and node 3 respectively. Likewise, node 2 broadcasts the pilot which aids in channel estimation at node 1 and node 3. In the third phase, node 3 follows the same procedure. By the end of phase 3, all the three nodes have their adjacent pair of channels, but the intersection of common source of randomness among all the three nodes is still empty set. For instance, node 2 doesn't have H13 and likewise node 3 doesn't have H12. So to bridge the gap, one of them is chosen to be the facilitator whose role is to help the node which cannot inherently observe the CSR. Like node 1 is the facilitator here. In order to explain the phase 4, we need to define some mappings and quantization as follows. In order to quantize the channel, we use this QAM constellation that has a one-to-one mapping with the algebraic ring as shown on the right. We make use of this quantizer and mapping to share the channel with the node which cannot see the CSR inherently. In the case of the user key generation, we don't need this quantizer or mapping as the CSR is directly seen at the two nodes. Please note that this quantizer is different from one which is used to synthesize the bits out of the CSR. We need the algebraic ring shown on the right in order to preserve the confidentiality. In phase 4, facilitator first quantizes his estimates of H12 and H13 in the QAM constellation and maps them to algebraic ring and sums them up in the modulo fashion. It then broadcasts the inverse QAM point of this sum in the ring to the two nodes. The other two nodes can retrieve the other unseen channel by first decoding the point in QAM, mapping it to the ring, and then performing modulo subtraction with the help of the known quantized channel at their end. After that, all the three nodes apply bit synthesizing quantizer to the chosen CSR either H12 or H13 and undergo consensus phase, where they check for the indices out of the guardband at all the three nodes and derive the key. Now one interesting question arises here. Out of the two channels H12 and H13, which one to use as a CSR? In the Venn diagram, we can see that there are three possibilities within a given coherence block. Either H12 is in consensus at all the three nodes or it is H13. There is one more special case where both the channels are in consensus at all the three nodes and either of them is a good candidate as the CSR. In the original paper, the author fixed the CSR to one of the two channels irrespective of whether the other channel is in consensus or not. But in order to enhance the key rate, we propose to use CSR opportunistically as follows. In the first two cases, when either of the two channel is in consensus, we simply use that channel as a CSR for that coherence block. But when both the channels are in consensus, we propose a selection criteria which overall improves the error rate. Here please note that as a consequence of this second theorem, we cannot use both of them as the CSR at the same time as the leakage to Eve is non-zero. The first theorem ensures the confidentiality feature of the presented scheme. That is, if we use either of the channel as CSR, it will give no advantage to Eve. So when both the channels are in consensus, we will use either of them to be the CSR. Now we present the selection criteria. So the basic idea is for the given two channel realization H12 and H13, the facilitator computes the respective probability of error when CSR is H12 and when CSR is H13. Then it takes the decision in favor of the one which minimizes this error. We illustrate the idea with an example. Here R denote the real part of complex CSR, superscript denote the channel and subscript denotes the node. For example, our H121 is the real part of the quantized channel corresponding to H12 at node 1, which node 1 acquired when node 2 broadcast the pilot. Likewise, our H131 is the real part of the quantized channel corresponding to H13 at node 1. In phase 4, as we know, node 1 broadcasts the modulo addition version of the two channel. Here phi is the mapping from a QAM to algebraic ring. Addition is over modulo 8 in this case, and phi inverse is used to map this back to QAM for efficient broadcast. So plus 5 is transmitted. Node 1, which is facilitator, now mimics the operation at node 2 and node 3 to retrieve the C subscript sum. It would build the Gaussian distribution on QAM points using the channel realization H12 at node 2 and H13 at node 3. On the right hand side, node 1 mimics node 2 while decoding R H13 as node 2 doesn't have access to it. Likewise on left, node 1 mimics node 3 while retrieving R H12. As we can see here, the value of R H12 is minus 3 and hence the variance of the Gaussian while decoding R H13 at node 2 would be less as compared to the variance at node 3 while decoding R H12 as the value of R H13 is plus 1. Although the actual variance would depend on the complex value of the channel, but for illustration purposes we have assumed that the complex part of both of them are the same or 0. Further, both the nodes do a modulo subtraction with the respective version of the channel they have. For example, on the right, node 2 has the knowledge of RH12, so it will subtract the sum by 2 units in the algebraic ring. As we also know that retrieved version should be plus 1, so the event of error occurs when this point is decoded as any point on the left hand side of the quantizer, as we are employing a two-level quantizer to synthesize bits. Likewise, we do this for the other nodes, and CSR, which minimizes this error, is used for that coherence block. The same algorithm is presented formally here. These two expressions are the same as discussed. In terms of key rate, compared to a fixed CSR scheme, we achieve a higher key rate as shown. These plots are for different values of bounds on initial error, which decides the guard band around the two-level quantizer, and for different values of M, that is the size of QAM constellation. In terms of error performance, the baseline is challenge selection, where decision is made simply by calculating the instantaneous SNR at the two nodes while retrieving the respective unseen channel. we can see that likelihood-based selection outperforms channel selection-based methods. Next, we will see another important aspect of key generation method, information reconciliation, where we try to correct the bit sequences without revealing information about the correlated sequence. There are multiple approaches to this. One of the most widely used is LDPC reconciliation, where LDPC codes are used in some way to secretly correct the bit sequences of all the three nodes. Let us suppose the reference key is the key generated at node 1, and our aim is to correct the sequences at the other two nodes. That is, depending on the CSR, one of them is the reciprocal node as it can see the CSR while probing phase itself, whereas another one is decoding node which uses the phase 4 of the algorithm to get the CSR. Facilitator first uses the key at its end to form a syndrome vector, which is simply the product of a parity check matrix with a key. The two nodes then use the syndrome vector and LLR equivalent of the CSR to agree on a key which is nearest to satisfying the constraints set by the syndrome vector by the usage of this message passing algorithm. For, the, for this purpose, we need LLR for the two set of nodes. At the reciprocal node, it is easy to generate the LLR given the joint PDF of the channel statistics, but in the later case, as decoding and algebraic subtraction is involved, we need some other way to generate the LLR. So the procedure is illustrated next. Suppose CSR is RH13 for this coherence block as other channel RH12 equal to -3 is in guard band, and node 2 need to generate the LLR for RH13 which is decoded as +7 after algebraic subtraction. As node 2 is decoding node in this example, it can't make direct use of joint PDF to generate the LLR. Instead, node 2 will hypothesize on all the points which are out of the guard band as potential candidates for CSR and will build some distributions on them. Suppose node 2 hypothesized +5 as the CSR. In order to do that, the facilitator would have transmitted phi of -3 plus phi of +5 and the inverse of this mapping to QAM, that is -7 in phase 4. This red distribution corresponds to that with a variance depending on the channel conditions, that is a complex valued H12. The red point is the corresponding PMF if CSR is +5. Likewise, node 2 will do this for every other potential CSR and will build these distributions. Next, as a part of phase 4, node 2 will do algebraic subtraction by 2 units. These bold circle denotes the shifted PMF. Now, as the actual decoded CSR is +7, node 2 will calculate the average probability of bit being 1 at CSR point, that is +7, by taking the average of PMF corresponding to the hypothesized point +5 or red bold circle and +7 green bold circle, as positive CSR is assumed to be quantized to bit 1 in the 2-level quantizer, and likewise average probability of bit being 0 is calculated. LLR is then computed as logarithmic of the average probability of bit being 0 divided by the average probability of bit being 1. Then this is fed to the message passing algorithm along with the syndrome sent by the node 1. The same algorithm is presented formally here. This expression denotes the average probability of bit being 0 or 1, where b can either take the value of 0 or 1. We compare the LDPC reconciliation based key generation against no reconciliation scheme and can see a significant improvement in terms of error rate for different values of m, that is the size of QAM and bounds on initial error that defines the boundary define the guard band around the boundaries. In conclusion, we first present a method to improve the key rate by opportunistically choosing the CSR. Secondly, selection criteria to improve the error performance. And at last, LLR generation method for information reconciliation is presented. Thank you.